MOSFETs, so metal oxide semiconductor field effect transistors. That's a pretty broad topic, and that's what I'm gonna talk about today. It is actually a type of lecture I haven't really done that much of. And one of the reasons for that is it is a pretty complex topic, and it's deep, and it's tricky, and it's difficult, and so on. But today, I want to go through the material that I created on MOSFETs. And this is meant to serve as a kind of a refresher if you've been through the topics before. So first of all, the metal oxide semiconductor field effect transistor is the fundamental component of most integrated circuits in the world. Everything that is digital runs on these MOSFETs. In principle, it's a three-terminal type of device. It has something called a gate, it has a source where the electrons come from, and it has a drain. And it's a three-dimensional structure. So the drain and the source, those are built into the wafer, like implanted with, in this case, donors would be, for example, phosphor. So you implant phosphor into the silicon surface, and you create sort of regions of higher doping, of more electrons, basically. The substrate is usually P- or some sort of P, so doped with bore. So that has an excess of holes. The length of an MOSFET is the distance from, well, let's call it the rough distance from source to drain. It's not exactly that. The actual transistor looks slightly more complicated than the three-dimensional picture I'm showing you now. There might be lightly doped sections on both the drains and the source. There might be halo doping. There might be more sort of complex engineering of the transistor. But in principle, it is the distance from source to drain that gives us the transistor length. And for the transistor width, it's, well, how wide is the gate or the drains, basically. Now, a wider transistor gives you more current. So, as an analog designer, we can play with both the length and the width to adjust what type of current we need and the type of sort of conditions that we need from our analog circuit. So what I'm going to do is I'm going to try to start slowly and give an opportunity to at least understand a little bit how MOSFETs works, and then we're going to go more deeply into the quantum mechanics, or maybe not quantum mechanics, but at least the effects of quantum mechanics. MOSFETs exist in multiple different flavors. For a specific technology, for example, SkyWater 130, there will be a 1.8 volt type of MOSFET. Both a type of MOSFET that is built from N diffusion, or N source, N drain, and P substrate, and also the flipped version where you have a P source, P drain, and N substrate. The difference between those two transistors is whether it's the electrons or the holes that is the dominant charge carrier. What we see on the left side here is an NMOS. So in that, it is the electrons that is the dominant charge carrier. So as we increase the voltage on the gate, the current from drain to source will increase, assuming source is lower than the drain. What we actually see in the arrow here is the direction of current. It's not the direction of the electrons. The electrons actually flow the other way. For the PMOS, there it's opposite. As we pull the gate down, so we again increase the gate to source voltage, but in this case the source is the higher potential. Then the MOSFET turns on, and there's a current flowing from source to drain. And in this case, we just note it as it's flowing into the terminal here. There you can see that there's a space between the gate and the rest of the transistor, and that's to illustrate that there is an oxide, an insulator here. So these type of transistors work through a effect called a field effect. So imagine it like this. The blue stuff, that's the free electrons, the electrons that can contribute to current. In the source and the drain regions, we have additionally, we have added phosphor atoms, which has an extra electron, and those are very easy to release from the bound state. So they're floating around. They're free electrons. And that means that both the source and drain are relatively low ohmic. But they cannot flow from source to drain in this picture. They actually do flow a little bit. We'll talk about that later. But in principle, there is not much current if the gate voltage here is the same potential as the source. As we start building up a small potential, so we increase the gate voltage, then something happens. So we can see that now there's almost maybe a little bit of blue underneath the gate, and these are electrons. These are electrons that now have enough energy to jump the barrier from the source side to the bulk, and underneath here there'll probably be what's called a depletion region, or a region that doesn't have that much mobile charges. But there won't be many. There'll only be a few. The currents will be very, very low. As we continue to increase the gate voltage, at some point, suddenly, relatively suddenly, within a few hundred millivolts, then there is a thin, like a few nanometer thin, sheet of electrons, of free electrons, that gets, I think the right word would be made, underneath the oxide in the silicon. It's not exactly at the surface, it's slightly below the surface. And that's actually determined by quantum mechanics, where the actual density of electrons are. Now, if you want to actually look at why is there this thin sheet of electrons, we have to go to quantum mechanics, and we're not going to go all the way today. But imagine this as a sheet of free electrons, which means as soon as we put a voltage differential on the source and the drain, then there will be a current flowing. Okay, but something interesting will happen if we increase the drain voltage past a certain point. Because if we increase the drain voltage, and in the beginning when we increase the drain source voltage, then the current will increase. It will actually increase linearly with the voltage. But at some voltage, if we can continue to increase the drain source voltage, then the current doesn't change that much. Because it turns out that this sheet of electrons, it sort of disconnects from the drain at a certain voltage, a certain drain source voltage. It disconnects from the drain, and now there will still be a current that can flow, because now we have a depletion region, or basically a region kind of like an insulator, where the electrons, well, it's not like an insulator, because the electron can still move if they get into that region, because there's a very strong field between the end of this blue section and the drain section. So they sort of get swept across if they get into that region. So the fundamental principle of MOSFETs is as you modulate the gate source voltage, something happens underneath in the silicon. And that something is an ability to control the current that goes from drain to source. And that we can use in circuits. Now, one of the more sort of simple circuits. Now you understand the basic principle, right? You turn on the NMOS by applying a high gate source voltage. And for the PMOS, you do the opposite as you apply, well, it's still a high gate source voltage, but the source is flipped, so it's sort of you have the source here at VDD, you actually have to apply a low input voltage. Now, if you do that, you make the region between the source and the drain conductive. And that means that we can make simple logic gates as you're seeing now. This is an inverter. And basically, it takes the input voltage and it inverts it to the output voltage. And this will be regenerative. So as soon as the input voltage crosses a certain voltage, maybe half a volt, if we have a modern technology with a 0.8 volt VDD, if it crosses half a volt, then the output will go to 0, because the NMOS becomes stronger than the PMOS. And with this, we can create logic gates. And really, the only logic gate that we actually ever need is the one you're looking at now. And I believe this is a NAND. So let's see. A NOT AND will have... Okay, now I have to think. I always have to think on these small things. But let's look at the pull down. So it's only when we have A and B that we get 0, right? If we have A or B at 0, then we get a 1. Yeah, so so this is a NAND. So when we have A and B equals 1, then we get a 0 out, and if we invert that, then it's only when we have 1, 1 in that we actually get a 1 out. Yeah, so it's a NAND. This is the only gate you need. Any digital logic can be made with a NAND equivalent. Okay, so now at this point, if you're a digital designer, you can stop the video and you can go on with your life, and you don't have to know anything more. It's enough. If you're in my course, then I do want you to know a little bit more, and I'm not going to try to take you through it. So if you go into the book, the Johnson Martin or the Carson Johnson Martin analog integrated circuit design, you will find equations for the current that is between drain and source at high drain source voltage. But there's not one equation, there's multiple equations. There's one that works in some region called weak inversion, and there's one that works in a region called strong inversion. These are the two ones, and you can see that both of them depend on something called a gate source voltage. So that's the actual voltage between the gate and the source. But we can also see that they depend on a magic thing called a threshold voltage. That's the VTH. And then for the current in what's called weak inversion, it also depends on the thermal voltage. So this is the KT divided by Q. And if you looked at the other sort of old refresh videos, then you will remember that if you ever see a KT divided by Q somewhere in the equations, then it's probably got something to do with Fermi-Dirac statistics. And indeed, it's quite similar to that. And actually, this is very, very similar to diode equations, or indeed bipolar equations. But there's also another equation for MOSFETs. And these are models of reality. So the real MOSFET doesn't exactly work like this, but it's almost. And we can see that the current is proportional to something called the mobility. That's the mu n. That's like, is it an acceleration constant? I don't remember the unit right now, but it's how easily do the electrons move. The gate, or the oxide capacitance, that's the COX. The width that we know from the picture earlier, the length, the gate source voltage minus this magic threshold voltage squared. So we had two different equations for the current that goes from drain to source. And why is that? So let's look at the weak inversion first. And there's really no way to look at this, I believe, without looking at the physics of the source, the gate, and the drain. And let's for now ignore the thing about the gate voltage. Let's only look at the drain source voltage and the fact that this is an NPN. This is a PN junction, which means that these are there will be diodes here. So from the substrate to the source, there's a diode. So the built-in field will be positive on the N side and negative on the P side, and vice versa here. So the diode direction, if you wanted to inject current into the bulk, it would go out the source or out the drain. So there's this parasitic diodes in the MOSFET. And what I've drawn here is the density of, well, roughly, the density of mobile charges. So in the drain region, for the electrons, N, it's roughly the same, the density of electrons is roughly the same as the number of dopant atoms. As we move into the P section, then we get less and less, and this is actually a log plot. So although it looks linear here, it is almost no mobile charges in this region between the P and the N, and that's why we call it a depletion region. It has not much mobile charge, much free charge. As we go into P section, then there's still electrons here. They're in the minority, so they're not that many. And how many is actually controlled by the intrinsic carrier concentration, Ni squared, or Ni squared, divided by the number of acceptor atoms that we dope the bulk with. And then as we move over to the N region again on the source side, we have a lot of electrons again. It's the opposite for the holes. So that's the red curve here. There's a little bit of holes in the source region, there's a lot of holes underneath the gate, and then there's a little bit in the drain region again. The reason I tell you about this is let's look at what happens in the energy band diagram. So here I have drawn a energy diagram. The y-axis, which I've forgotten to include, that's the energy. And the x-axis, that's just a horizontal line in the x direction. So it's sort of source, gate, drain, same thing. Now, the fact that the carrier concentration and the doping is different here means that there will be bending of the bands. So remember here, when we put p-type silicon together with the n-type silicon, the Fermi levels have to align, which means that the conduction band, which we're looking at here because we're looking at electrons, that has to have a bend in it. There will be bending of the bands. And that band bending is depending on the doping. And that's this sort of built-in voltage that we get. So yeah, I think I have that later in the slides, but we've gone through that before, how to get to the built-in voltage. Now this energy barrier, like Q times this built-in voltage, it's possible for electrons to go in the source, for example, to jump up into the energy level that is needed to be free in the P region. It is possible, but it doesn't happen for many of them. And here we come in with the Fermi-Dirac statistics. The probability of, not the probability, but the difference in carrier concentration, really, between the source side and the gate side, that's going to be also given by whatever potential we put across this junction. And the way those carriers change will be proportional to an exponential voltage. So if the barrier is high, there will be very few electrons that actually are able to enter the energy high enough to be able to be free in the P region, or cross this energy barrier to get up this hill. It's quite hard for them to get out up the hill. Now, assuming the doping on the drain and source side and the P doping is the same, then the energy barrier is the same on both sides, which means that it would be equally probable that an electron goes from the source and it jumps up to high enough energy to get across the barrier into the P region. Once it's in the P region, it can drift across, and here there will be a probability that it actually recombines with the holes that is in the P region. But that takes a bit of time. And as long as the distance is quite short, that probably doesn't happen. If the transistor is very long, then most of those electrons combine. But as we go into, as the electron traverses across the P region, eventually it will see a potential that goes the opposite direction. So here it's positive on the N side and it's negative on the P side. Same on the other side. Positive on the N side, negative on the P side. Which means that as soon as it gets close to the drain region, it will actually be accelerated across by the field, and it'll end up in the drain region. Now, as long as we don't apply a voltage between the source and the drain, there will be a continuous flow of electrons, sort of equalizing the Fermi potential. Because as soon as there's any sort of difference in the potential between source and drains, there will be currents flowing here, because there's slightly more currents, slightly more electrons, for example, that get injected at the source and then end up at the drain, and so on. The potential changes, and so on and so on. And what's important is that electrons actually flow in both directions, because there will be electrons as minority carriers in the P section, and they will roll down the hill. And same on the other side. So injection happens at 1 and 4, and then rolling down the hill happens at 2 and 3. Okay. No current really flows, because the average movement of electrons is 0 in this case. They are still moving. They are still crossing the barrier, but average current is 0. Net movement of electrons is 0. Now, change the voltage on the drain. And if you remember that changing the voltage in an energy band diagram for electrons is equivalent to reducing the barrier height. Okay, so now the source barrier, that stays the same. That's given by the doping. But now we've added a voltage on the drain side, and we've reduced the barrier. But actually, that's increased the barrier to the P side. So that means that there's less electrons that come in from the drain side. And now this balance is disturbed. Now there will actually be a net movement of charge from the source to the drain. And the net movement of charge will be a current. So simply by changing the drain voltage here, we are sort of providing a leakage path from source to drain, even though we haven't got a gate voltage yet. This is the origin of the subthreshold leakage, the leakage that you have at zero gate voltage. Okay, but as you modulate the gate now, what's actually going to happen is that this energy barrier height is going to change. It's slightly complicated how it changes, but in essence it does change, which means that as I reduce the barrier between source and the energy barrier underneath in the substrate or the bulk, then more electrons gets injected. And this is actually an exponential relationship. So as I increase the VGS, then the current increases exponentially, and very similar to a diode. Now this threshold voltage, we'll get back to that, don't worry about it now. But we can see that if we insert a, let's say we insert a gate source voltage that is equivalent to the threshold voltage, then this expression becomes 0, and e to the power of 0, that's 1. So then at the VGS, where we have the threshold voltage, then the current that we have is actually this ID0 times the width divided by length. So this ID0 is sort of a parameter for the transistor that we could measure actually, as long as we put the gate source voltage at the threshold voltage, whatever this threshold voltage is. Okay, so this is the behavior of the MOSFET in weak inversion, or where the threshold, where the gate source voltage is quite a bit below the threshold voltage. Now we can also compute a transconductance based on this equation. We can take the derivative. So the derivative would be, what is it? The derivative of the current divided by the derivative of the VGS, and that becomes the transconductance. And we can see that that actually is a kind of like it's the current divided by N times the VT, or the thermal voltage. I see I have used UT and VT and interchangeably, but you're smart. You can get that. Okay. Now, fundamentally, the behavior of the transistor changes as we increase the VGS. And now we're talking about the bulk effect. It's going to be similar. This change in barrier that I talked about, it is similar. But now, instead of looking at the cross-section, sort of side view of the MOSFET, now we're looking at sort of well, it's more like a cross-section where we're looking, the x-axis here is the depth. So we have sort of a slice through the gate and the oxide and the bulk, and the where they're more in the right direction, I hope it'll be for you too. You go, the deeper in the silicon that you go. And what we're looking at now is a invented image where we have a metal gate, where the Fermi level of the metal gate is actually such that it aligns with the Fermi level of the silicon. I don't think that's actually is necessarily possible, but let's ignore that for now. Usually there's a slight difference in the Fermi levels, and then you get a work function difference, and that modulates with threshold voltage. But in principle, the Fermi level of the metal gate, assume that aligns with the Fermi level of the silicon, and we can see that in this case, since the Fermi level is close to the valence band, then we have a p-type semiconductor. We have an abundance of holes. There will be mostly holes here as free carriers. Okay, now increase the voltage on the gate, and increasing the voltage is reducing the energy. So in this case, we pull the energy down. Now, this change in voltage has to disappear at some point. And we're pulling the oxide down. We'll lose some voltage across the oxide, but not that much. But what actually happens is we're pulling the surface of the silicon in voltage or in energy. It's more an energy barrier type of thing. So we're modulating the bending of the bands. So both the conduction band and the valence band will bend in energy closer to the surface of the silicon. And what then happens, of course, is that the amount of holes in the valence band now reduces because there's a larger distance to the Fermi level, while the amount of electrons in the conduction band, that increases because the distance to the Fermi level is reduced. Now, as we go deeper in the silicon, then we're back to sort of intrinsic silicon. So initially what happens is that we'll deplete the area underneath the gate, underneath the oxide, of holes, holes as a free carrier. And after a while, it'll be replaced by electrons, because as we continue to pull the voltage on the gate, at some point, most of the available states will be filled. Because if we remember back to how we compute the number of or the density of charges, we take the integral of the conduction band to infinity of the density of states, and we multiply that by the Fermi-Dirac or the Fermi function. Now the Fermi function, if we're at the Fermi level with the energy, then that's equivalent to 50% of the states being filled, which means that when our conduction band now goes beyond the Fermi level, below the Fermi level, then most of the states, available states in the conduction band, will actually be filled. And now we have created this magic sheet of electrons. Okay, so if you actually wanted to compute, and let me pull that up. Hopefully, I'm connected to the VPN. Let's see. Okay, so let's see. I wanted this one, didn't I? Where is it? Where did it go? That's the one. Oh, it's over there. Okay. What I wanted to show you was that if you start with Schrödinger, and they do that in this link, you can check that in the notes. Here you go to here you can see that's Schrödinger. Okay, this is the Hamiltonian in Schrödinger. So you start from quantum mechanics, and then you compute what's the wave function. So what's the wave function that you get? I think that we're looking at it right now. I think this is it. Yeah, so this big function is the wave function, and the wave function, the absolute value of the wave function squared, is the probability distribution of electrons. Now, I'm not going to go through the function. That's not the important part. The important part is this figure. So here we have the same type of figure. We're looking from the surface of the silicon and into the deep of the silicon. And what we can imagine, or what we can observe, is that from the classical description, where I say we get this energy band bending below the Fermi level, we would expect that most of the charges are located at the surface. This is sort of the charge density. But it turns out that when you actually compute with with Schrödinger and compute the wave function that you get in these conditions, you end up that the most of the electrons, the density, is slightly below the surface, and it's in a very, very thin sheet. So the thickness of this distribution is extremely thin, a few nanometers maybe. So that means we get this thin sheet of electrons. So in a very, very, very real sense, MOSFETs are a quantum mechanical device, which is kind of cool. Okay, but what if we didn't want to worry about all this quantum mechanics stuff? You can, if you take solid state physics, you have to, and you have to compute the wave function and blah, blah, blah. But we're analog designers. We don't necessarily need to understand all the details and be able to compute the density of states and so on. but we do need to understand the behavior. So if I take a random transistor in SkyWater and I sit down and I try to see, okay, how does this thing behave? Well, let's have a model. Our model is what you're seeing on the screen now. I have this gate source voltage that I can apply between the gate and the source. And what if I just look at the current that goes from drain to source? And that's going to be some function of the gate source voltage and the drain source voltage. And how does that function look? So if I modulate the gate source voltage, here we can see the current and we have a log y-axis. And here we can see the change in behavior. So initially, at very, very low gate source voltage, the current still changes. And that is reducing this energy barrier. That's reducing the energy barrier so we get more electron injection from the source. As we get closer to this magic threshold voltage, then the behavior changes. It's no longer just the reduction of the energy barrier. Now we've created a sheet of electrons, and we can see that the increase in current as a function of the voltage, that changes. It goes from an exponential behavior, so linear in this, so it's exponential current for a linear increase in voltage, over to something that increases less rapidly, a square law. And eventually it does other things when we get a really high gate source voltages. But this is sort of the behavior. And that also means that these two equations that we have, one for when the gate source voltage is quite low compared to the threshold voltage, and one when it's quite high compared to the threshold voltage, gives us different regions. And in the middle, there's a mix of them. So that means that fundamentally, for the transistor, we can define a parameter that we can call V effective. So if the V effective is 0, then we're sort of at the boundary between what we call weak inversion or subthreshold and strong inversion. So that's this moderate inversion. If we're a lot below that, then we're probably more into just modulating the energy barrier, and it's in the electron injections from source into the substrate and the free electron states there, that energy barrier, that is the dominating effect. And that current that flows is actually more sort of a diffusion current. So what I mean by that is when you inject the electrons from the source to the bulk, then it's simply because the concentration of electrons is higher closer to the source that they sort of diffuse away. And some of them will reach the drain, some of them will recombine and disappear. As we proceed up in strong inversion, then the behavior changes a bit, because now we have a conductive sheet of electrons. And in that conductive sheet, we can have a voltage drop, which means that it's more a drift current. So in transistors, it's a combination of both drift and diffusion currents, and those are fundamentally two different currents. It comes from Schrödinger in that too. So, quantum mechanics, right? Okay. In weak inversion, I've said this before, but actually, maybe I didn't say that earlier. So we have this function for drain source. That is a function of the V effective. But that only applies if the drain source voltage is larger than about 3 thermal voltages. And that comes back to this energy barrier that we talked about on the weak inversion. Let's actually go quickly back through that, because I didn't mention that. As you start at the same potential on source and drain, then the current is not defined by this exponential behavior, necessarily. But as we increase the drain voltage, and maybe only at about 3 thermal voltages, then there's almost no injection, comparably, from drain to the substrate of electrons. It's almost nothing compared to what's injected from source to the bulk. So that's the reason for this usual rule of the currents given by this equation here. So ID0 W divided by L, e to the V effective divided by N, which N is a number, 1.5-ish. That only happens if the VDS is larger than about 3 thermal voltages. Moderate inversion, that's actually, in these days, in modern technologies, that's where we spend most of our time. Sorry, it's really hard to put transistors into strong inversion these days in 22 nanometer and further down. So these days also the transistor models that we use, the BC models, they're actually pretty good. So there's no problem in moderate inversion. There is a very big difference between moderate inversion, strong inversion, and weak inversion when it comes to the transconductance and what we call the GM divided by the current. But there's nothing wrong with putting transistors in moderate inversion. Maybe one thing that is a bit wrong is that if you don't have very good control of the gate source voltage or the behavior of size of the transistor or whatever, then it becomes a bit tricky because the behavior might change a bit. But nothing's wrong with moderate inversion. As for strong inversion, here we have, as I said before, we have this V effective squared times a half, and depending on the drain source voltage, here something happens. I don't think I spoke about that, but let's look at that in a bit more detail. And actually, also let me include the case where we have a gate source voltage that's less than 0, because in that case, there will actually be holes all the way up to the silicon surface. They won't be pushed away by this voltage. And in that case, there can be an accumulation of holes actually close to the surface because you're bending the bands in the other direction, and you actually increase the number of holes in the valence band. Not that much, but it depends on the distance between the Fermi level and the valence band energy. But in this case, you can actually have quite a bit of capacitance between the gate and the bulk. As we increase the gate source voltage, we initially start by depleting the holes in the valence band, and you increase the number of electrons, and you create this channel that we talked about, this thin sheet of electrons underneath the channel. Now, the definition of this threshold voltage, this magic threshold voltage, is really funky, I think. It's just defined as, okay, it's when the density of electrons in this inversion layer, this sheet of electrons, when the density of electrons there equal the density of holes far away from the the channel or the inversion layer, that's what we call the threshold voltage. So when the density of electrons here equals the density of holes a bit further away, that's our threshold voltage. Now, how do you measure it? It's not that easy. So, yeah. Anyway, where were we? Drain source voltage. Yes. So that means that as we modulate the drain source voltage now, we can actually see that initially the current increases with the drain source voltage, but at some point it kind of slows down. It still changes a little bit, but not that much. So what's the reason for that? Well, it turns out that as we increase the drain source voltage, then at some point we create a condition that is quite often referred to as pinch-off, because in this conductive sheet of electrons, there is a voltage drop. It's a resistor, kind of. So the voltage changes as we go along the channel. And at some point, when the VDS is high enough, then the point underneath here, it doesn't really go beyond the V effective. And that means that the rest of the voltage is sort of across this small region of depleted carriers. So we have the point here, the end of the channel, that's roughly at a voltage that we call VDS sat, or about the V effective. And then the voltage across the depletion region, that's going to be the drain source voltage minus this VDS sat. So now the amount of carriers that gets injected at the source, or the current in this sheet of charge is not really that dependent on the drain voltage anymore. Because as you change it further, all you're really doing is modulating the voltage across this depletion region. That does change the length a bit of this depletion region. So you're moving it a little bit. That's called channel length modulation, and that gives you the output resistance of the transistor, in addition to a few other effects. But yeah, that's how it works. So if we imagine this extremely thin sheet of electrons, then when we accelerate electrons to free electrons in that sheet, and they reach the depletion region, they will see this quite high field and be swept across. So here, there's going to be a high field, and there's also going to be a high vertical field, and so on. Okay, that's the principle of the transistor. But let's look at what happens at low frequencies. So in electronics, we are dealing with nonlinear circuits. They're highly nonlinear. MOSFETs are a highly nonlinear circuit. But it's not that easy to analyze nonlinear circuits. So one of the things that we can do is sort of put up roughly the voltages and so on. And then we can look at what's called a small signal analysis. So look at a small change in gate voltage. What happens then? And that's what we're doing here. We take the derivative of the drain source current as a function of the gate source voltage, and then we can get the GM. And similarly, we can take the change in current as a function of the change in VDS, and that's more equivalent to an output resistance. And both of these we can put into a small signal model, a low frequency model. So as we change a little bit the gate source voltage, we can predict how the current will change, and we can predict the output resistance. So if we look at the transconductance, and this is going to be strong inversion. So we have this minus Cox W divided by L. We have the V effective. We have the square law model. And then we can rearrange it a bit. We can take the derivative, and the derivative of this current here with respect to VGS gives us this L times V effective, or you can write it also a slightly different way, or you can rearrange things, and you end up that in strong inversion, the transconductance is roughly given by 2 times ID divided by V effective. And that's a useful equation, because now I can say, okay, if I know my transconductance and I know my V effective, I can predict the current, or vice versa. If I know my current, I know my V effective, I can predict the transconductance roughly in strong inversion. So at a high gate voltage when we have the inversion layer. Now, same thing for changing the VDS. We can take the derivative with respect to VDS, and now we have to include the other parts of the function in the drain current that I had earlier on that includes the effect of VDS. So this is actually, it includes the effect of VDS. And we left with that the conductance between drain and source, that's roughly proportional to some sort of gamma, a factor, a number, times the drain current. So as you increase the drain current, then this resistance in our small signal model actually reduces. And now we can look at what's called the intrinsic gain. So how much bang for the buck can you get from a single transistor? And that's usually given by the transconductance divided by the conductance between source and drain. Now, maybe I should mention that. So conductance is simply the inverse of a resistance. It's how much current flows between 2 nodes given a voltage. Or the current is given by the conductance times the voltage between 2 nodes. Transconductance, however, that's slightly different, because that's the current between 2 nodes depending on a voltage somewhere else. Transferable, or I don't know what that actually means, but that's the actual statement of a transconductance. It is the conductance between 2 nodes. So the current times a voltage somewhere else equals, no, the transconductance times the voltage somewhere else equals the current between 2 nodes. Transconductance. And we can see that that's roughly given by 2, if we take the intrinsic gain now, GM divided by GDS, then we get about 2 divided by, let's say, V effective. So as we increase the gate source voltage and go higher and higher above threshold, then the gain of our transistor actually goes down. Okay. Now, there's an additional effect in transistors, and it turns out that the threshold voltage actually depends on the potential of the bulk, and specifically the potential between the bulk and the source. So there is an additional, call it a current, that also depends on the bulk source voltage. And this is sort of a more complete model of the transistor. And that means that if you have you can actually see this in the temp sense videos that I made, because there I have a transistor that has a different source potential than the bulk, and you can see that that actually has an increased, you need a higher VGS to get the same current. Okay. For high frequency we need to include capacitors. And it's not that big distances between the gate and the source and the drain and so on, so that there are these capacitors. There's the gate source voltage, of course, that because we have this huge oxide, very, very thin oxide between the gate and the bulk, and that's going to give us the CGS, the gate source capacitance. There's going to be probably a source bulk capacitance, because that's a diode, so that's a nonlinear capacitance. Same for the drain bulk. It might actually not be a diode in 22 nanometer FD-SOI or in the FD-SOI or in SOI processes. There is no diode between drain and the bulk, but yeah. And then you have an overlap capacitance between the gate and the drain often. But the full thing here is what we call the small signal model of transistors. It's not that common to use this for analysis. It's what we teach you. It's for you to understand what's important. Yeah, it's rare that we put up a full circuit with those, but you actually do have to do that if you want to compute the high frequency gain, for example, of an op-amp. Usually. Or you put it into the simulator and do it that way. But if you want to do it analytically, you can do it with the small signal models. Sometimes, though, like diff pair is better analyzed with the T model of a transistor. Yeah. Anyway, so here I'm just illustrating where the capacitors are. We have the CGS. This is a transistor in strong inversion. So we are actually going down to this would be the capacitance between the gate and the inversion layer. And then there will be a capacitance between the source and inversion layer and the bulk. That would be this diode. And the same for the drain. And then there's going to be an overlap capacitance between the gate and the drain, because usually the drains go slightly underneath the gates. Now, we can estimate these. For the CGS, it's roughly the width, the length times the C oxide. That's if we're at the 0 drain source voltage. So that means that we haven't pinched off the channel. As we pinch off the channel, so then we reduce the capacitance. We reduce the capacitance, and we can see that the gate drain capacitance, that doesn't look very big, but we'll look at that later. Now, the source and bulk in bulk process, the source and bulk capacitance in the bulk process, like SkyWater, those are both depletion capacitances. Those are the nonlinear capacitances that have between, across the depletion region. So when you have a P and then you have an N. And the capacitance is then given by some sort of area of the source and the channel, in this case, and this junction capacitance, which is some number divided by a function that goes as the square of the voltage across it, where the built-in potential you can see down here. So here we can recognize the number of acceptor dopants, or density of acceptor dopants and density of donors, and the intrinsic carrier concentration and thermal voltage. So just a quick mention of the CGD. So the gate drain capacitance in our NMOS will be between the gate and the drain. Now, our transistor, we'd like them to have high gain, usually, at least analog faults. We like them to have high gain. But if we hook up a capacitor between the output node of an amplifier with inverting gain and the gate, or the input of an amplifier with inverting gain, it actually turns out that when you look into the gate, in this case, the Cin, that actually is going to appear to be larger. It's 1 plus the gain of that transistor times the capacitance, which means that depending on the gain on the transistor, that apparent capacitance of the CGD might be a lot bigger than you think. So sometimes you have to think about it. Weak inversion, I guess most of this we've covered before, but as I said, here we're talking about diffusion currents, because we're injecting mostly electrons from the source if we have a high drain voltage, and then they diffuse across. But interestingly, the transconductance turns out to be slightly higher. So when we're looking at the bang for the buck, or the GM divided by ID, so how much transconductance do we get for a certain current, then the most bang for the buck is actually achieved in subthreshold. So we can see that in subthreshold, it goes roughly up to 1 divided by the N times the thermal voltage, which is about around 25, a bit over that. while when we increase the current and keep the dimensions of the transistor, which is sort of increasing the gate source voltage and eventually increasing also the V effective, we can see that the bang for the buck reduces. So we get less transconductance for the current. Now, in my standard libraries that I use, I usually pick a couple of points on this curve. I've chosen GM over ID of 15 and GM over ID of 10. And that's roughly just, it's not completely in strong inversion at GM over ID of 10, and it's not completely in subthreshold at the GM over ID of 15, but it's two numbers. Yeah. Okay. A few other effects that we have to think about in transistors. It turns out that electrons have sort of almost like a speed limit. Average speed limit. And that means that they cannot move as fast as we want them to in this sheet of electrons underneath the oxide. There is a speed limit. Now, that speed limit is about 10 to the 7 centimeters per second. Normally, the speed would be given by the mobility times electric field, which is the same as the mobility times the derivative of the voltage divided by the distance. And it's actually from this that we can look at the square law model. If we take the charge in the inversion layer as the oxide capacitance times the V effective minus the position in the x direction in the channel, then, and we have the speed, we have this L factor, then the current is actually just the width of the transistor times the charge times the speed of electrons, right? So how many electrons move and how fast, that gives us the number of charges per second through this channel. And the width is just the width. The wider it is, the more electrons can flow. Now we can rearrange that a little bit, extract this L factor, and look at the speed, insert for the speed with the mobility and the dVdx. And we can move the dx on the other side, and then it could integrate this. We can integrate it from 0 to the length of the transistor. And the other variable, we could integrate from 0 to the drain source voltage. And if we do that, we end up with this equation. Actually, yeah, this equation. And we can see that equation is quite similar to the square law model. If we insert for VDS equals V effective, then we get V effective squared here minus half of V effective, which is half of V effective, and we have our square law model. So this is how we derive the square law model for the transistor. And it's roughly correct in the right region. There's complications here, but now when the speed is limited, so we had the speed here, when the speed cannot go faster, it's no longer given by this function, the mobility times the derivative of the voltage divided by derivative of the voltage as a function of distance. Then we have to limit it, and that is introduced with sort of a change in the mobility. Effectively what this does is when we insert it and we do the calculations again, it turns out that now we don't have necessarily a square law model anymore. It is slightly less than square law. Eventually, it might actually be only proportional to the effective. So eventually, we don't really get much more current, or the square of the small signal current. No, the square of the small signal voltage is no longer proportional to the current. Okay, what about holes? I've only talked about NMOS and electrons so far, but it's the same thing for holes. The only difference is that for PMOS and holes, everything's flipped, but holes move slower, which means that the currents that you get in PMOSs is less for the same voltage. It's about, well, 3 to 4 times on that order of magnitude, depending on technology. Other things. Well, we have been on this journey for the last 70 years of making things smaller, making things ultra small into the, I guess these days, into the 2 nanometer technologies. And we are approaching definitely such that quantum mechanics comes into play for our transistors. Now, back in, well, I guess this is almost 15 years ago. I think it was 2009. I had the opportunity to write a paper. I only wrote a small section, and my section was not that important, but Lanny is a analog designer. He's been a consultant now for many years, and he's an ADC designer. He's one of the guys that made the ADC in Hubble, and he knows his stuff. So he wrote together with Tron and me and Ken Martin, the guy that wrote the book. We wrote a paper on analog and integrated circuit design in nanoscale CMOS technologies, and in that paper there's this nice picture of a transistor. So you're seeing the same thing here. We have the source, we have the drain, and this is, remember, this is 15 years ago, so the transistors today look even more complex. But there is a source and drain that's going to be raised, that's going to have also silicide inserted, maybe germanium, to reduce the conductance. And there's going to be a lightly doped section, sort of transitioning over to where we have the channel region. There's a oxide, that can be silicon oxide. These days it's usually maybe even hafnium oxide, or like a high K metal gate, or high K oxide and a metal gate. And yeah, so this gate material might be polysilicon, it might be metal, and then across the transistor maybe you have a cap layer to strain, to pull the silicon. There might be halo implants to reduce the amount of electrons that can be injected at high drain source voltages. And there's a bunch of parameters, which means that it is impossible today, realistically, to predict with a piece of pen and paper accurately the currents that's going to flow in your transistor. We need simulators, we need models, we need the foundry to extract all these parameters and give us good SPICE models for how to predict the currents. So, a couple of the effects is one's called drain-induced barrier lowering. If we look at the, this is voltage, it should really be energy, but you can just take the voltage, multiply it by the charge, unit charge, and we get energy. But here we can see that the energy barrier that we have for the electrons to go from source to bulk or the channel and down again, that can actually be modulated by the width. So if we make the transistor really, really small, then the energy barrier on the top here doesn't really necessarily go that high. There's a bending. And what can happen is, as we increase the VDS, which is reducing the energy, we can pull down the energy barrier at the source side. And this is called drain-induced barrier lowering. So as we modulate the drain voltage, the actual number of electrons that get injected from the source to the bulk, that increases. And that is the same as a resistor. So as we change the drain voltage, we get more current. So this is, in addition to the channel length modulation, one of the effects that modulates the current as a function of VDS. Then we have well proximity effect, and this is the effect that when we actually dope these larger sections for PMOS, for example, we inject donors into the p-type silicon. We are making a n-type silicon in a p-type material by injecting donors. Now, this is usually done by ion implantation, so you shoot the ions down into the silicon. You will have created silicon oxide protection layers on the side to pattern where you want the ions to be implemented, because you're shooting on the whole wafer. Now, some of these ions will scatter off this interface. You might hit the walls, and then what ends up happening is that close to the wall edge, the carrier concentration, or the number of dopant atoms the number of dopant atoms increases, which means that the carrier concentration close to the edge increases, which means that the threshold voltage increases. If you have a transistor that is closer to the edge than another transistor, the closest one to the edge will have a higher threshold voltage. So if you care about the threshold voltage of a transistor, you better place them away from the edge. Now, away from the edge is about, depends on technology, but let's say 3 micrometers. That's usually enough. Stress effects. Well, you saw back in the equation that we have mobility. Now, the mobility of electrons and how easily electrons move, it's directly related to the mass of the electrons. And if I remember correctly, the effective mass of electrons is related to the curvature of the band structure. So how the energy bands in the actual silicon unit cell exist, or how the energy levels change as a function of distance. Now, as we strain the silicon, the band structure changes, which means that the mobility can also change. And that's one of the effects that we can see with transistors as we strain in for a PMOS in the Vz, so that's in the direction of the width. And that might be good for PMOS to make the current higher and good for NMOS. But if you compress it in the y direction, so put strain that way, I guess, then it's okay for PMOS, and it's not that good for PMOS, but it's good for NMOS. And then for compressing the FX, that's really bad for NMOS and good for PMOS. And the reason it's different for PMOS and NMOS is because there's a difference between having holes as a majority carrier and the electrons as majority carrier. And how the band structures behave, well, that's dependent on the valence band and the conduction band. And the conduction band and the valence band might change differently depending on the strain. So, and we're really talking about strain here. So physically pushing on the PCB, if you do your layout wrong, like you have your current mirror with one transistor in this direction, and then you rotate the other transistor, and you do it for PMOS, then you can probably measure that current mirror or current changing as you apply stress to the PCB. I've seen that. Gate current. This is not that big a problem anymore. It used to be horrendous in 65 nanometer because we had the silicon oxide when we thinned it down to a few nanometers. And then we started getting into the direction where the electrons or the carriers, both the gates and the channel, well, the wave function for that particular free electron, it actually extended beyond the gate oxide, which means that the electrons could tunnel through. There will be a tunneling current through the gate. That is one of the primary reasons for why for transistors these days we have actually increased the thickness of the gate oxide, but using now a different type of material, so a high K, something that has equivalent permittivity. Yes, permittivity to silicon, effectively. So a thin, it's higher permittivity than silicon, but effectively the electrical thickness of the oxides seems to be the same. Something like that. Anyway, it's a thicker material, means less tunneling current, less of a problem with gate leakage. And I think, no, one more, hot carrier injections. Yes, okay. So this is something, these are the bad things that can happen to your transistor. This is the reason why the voltage on leading edge processors is sort of limited to maybe half a volt or something, or 0.8. So as we increase the drain, the field in the depletion region can actually increase so much that we can get what's called an impact ionization. So the electrons accelerate to such high energies that when they impact with the crystal lattice, or they scatter off this crystal lattice, they can actually knock out a new electron from a bound state. So they can free an electron hole pair. Now what you can actually get happening here is that can happen multiple times. So that new electron can then be accelerated again and generate a new electron hole pair. And the bad thing about these electrons is that in this depletion region close to the surface, there's also pretty high field from the gate, which means that we can inject electrons into the gate, and that can actually over time let's see, would that reduce? I think it's, yeah, no, it's going to increase. It's going to increase the threshold voltage. So you have to increase the gate voltage in order to compensate for the stuck charges that you have in the gate. And eventually you might actually also damage the gate oxide effectively. Or worst case, yeah, that's a different condition. We'll talk about that next time. And then there's also something called channel initiated secondary electron. And that's where you generate an electron hole pair. The hole, in this case, you have lifted the source quite high compared to the bulk. This usually happens in cascodes and all the type of circuits. And there's a high electric field from this depletion region down to the bulk region. Now the hole can accelerate down, and then if it reaches impact ionization energies, it can knock out at a bound electron. And now that electron will see a very, very high electric field, and then you can get injection into the gate again and degradation of the performance of the transistor. Apologies. So all these things lead to a problem for analog designers with variability. So imagine we make a circuit that looks something like this. It's a current mirror. We have an off-chip resistor, and that we can make as precise as we want. And we want to provide 1 microamp. So we take our transistor, we measure the VGS, we can control the VDD maybe, and we can tune in the resistance. So first of all, we have to make these two transistors equal, because what can actually change the current I2 here? Well, if we change the VDD, it's going to change because the gate source voltage. It's going to change because of systematic variation, so the layout effects. Process variation, temperature variation, random variation, and noise. We're going to go through them. So voltage variation. Obviously, if we change the VDD, then, but the VGS might, well, it's going to change a little bit since we change current, but the current is given by VDD minus the VGS divided by R. So as we increase VDD, that increases the voltage across the resistor, changes the current, and that's going to change the VGS, but not as much because that's a square law, potentially, or it might be exponential actually. So we need to keep VDD constant, but then we have systematic variation. So in our equations, as I said, if we have different current direction with mobility, or indeed also if the current in the silicon is in different directions, well, then the electrons are not going to see the same band structure. So it's only if you have a repeating pattern and you have the current going in the same directions that you'll have match of the current. Now, if the source voltage is slightly different, so we have resistance on the source, then it's going to be different. And if the bulk is different, well, then it's going to be different. And if we have one transistor close to the edge of the well, you're going to have a problem with the well proximity factor. And if the stress effects are different, then you're going to have different currents. And here, stress could be you have a metal wire across one of the transistors, you don't across the other. So there's so many things that can change our device. And then process variations, right? So all these different factors, the UP, the COX, the width and the length for that matter, those will change. So when we make our circuits, we have to simulate in typical slow, fast, what we call slowish, fastish. So slow, fast, fast, slow. And these 5 corners plus what we call Monte Carlo for local mismatch, that gives us a good idea of the solution space of what we're going to get back from the foundry when we get our circuits back. And that's really the job of the analog designer. So one way to fix process variation, that is to trim. So we could always fix whatever varies in the mobility and so on. We could have an external resistor that we tuned to get 1 microamp. But here just measuring is a problem because any multimeter or instrument usually has an input resistance. So measuring the voltage across this resistor and then tuning the RVAR here, that will also, there will be some current that goes into the voltmeter. And like my Solea logic, that has about a mega ohm input, so input resistance. So you have to be careful with even the calibration. Now temperature variation is also a problem because the threshold voltage here, the mobility is going to change with temperature. The threshold voltage is going to change with temperature. And yeah, that will change our voltage across the resistor. So also the funny thing is with the transistors, it's quite hard to figure out what's fast and what's not, because mobility increases with temperature, so it makes the transistor slower. But at the same time, the threshold voltage decreases at high temperature, which makes the transistor faster. So usually when we talk about fast and slow corners, we're actually talking about a fast corner. We're simulating at high VDD and we're simulating at high and low temperature, both, because we don't know which one is worst. And the same for slow corner, you simulate at high and low temperature. There's actually usually a point for inverters that we call sort of zero temperature coefficient, where if you have the right VDD, then the speed doesn't really change with temperature. Okay, so how do we fix this? Well, if you need stability over temperature, you need a band gap, and we're going to look at that. Now, random variation, well, these length and the threshold voltage, we are injecting dopant atoms. We're physically sort of pushing dopant atoms into the diffusion. And obviously, we can't put the same number every time into every single transistors. There will be variation. One will have one more and one will have one less. That's just how it is. The same for the width and length. There are limits to the resolution that we're using with lithography. I mean, most of the technologies that you use, that we develop today, use 193 nanometers, so our resolution in XY direction on the wafer is quite limited. We do have quite fantastic mathematics in order to improve that by using what's called a pre-distortion, or you actually calculate the interference patterns of the light before you expose the wafers through the mask, so that you pre-compute, because we know how light works, we pre-compute the patterns that would be correct in order to get the patterns that we want on the wafer. But even that has a limit, and we end up with double patterning and triple patterning with putting multiple masks for the same layer and so on. And well, yes, we have extreme ultraviolet, but that's insanely difficult. But in all of these technologies, we will end up with variation in widths and lengths. So, we have to deal with mismatch, and we have to simulate that. Now, Pelgram was a guy that wrote the paper on mismatch. He has that, I guess, maybe the model named after him. So for any given technology, there will be a factor that tells us how much millivolt or current change do we have in a parameter. And that's a function of the area, and then there's also a function of the distance between parameters. Usually, we only care about this first thing. So we have a parameter, which divided by the WL gives us the variance. So here we go into which region is it actually best to operate transistors in, because we can set up a general model for the variance of the drain current over the drain current as a function of the variance of the threshold voltage and the variance of this mobility and Cox and W over L. So we can see that in the function here we have GM divided by ID. And we know that GM divided by ID has a huge difference between weak inversion or subthreshold and strong inversion. So we can actually figure out that for our current mirror, in order to improve the standard deviation of the current over the current, so let's assume that the standard deviation there is about 10% of the current. Let's say we want 5. Then we actually have to quadruple the size in order to get the same thing. So we can increase the area, but that quickly runs out of steam. It's quite hard to get it much better. So low mismatch requires really big devices unless you have other tricks. So there's also something that we can do in this equation, and then that is to make the GM over RDD as low as possible, because then that gives us less variation, right? So if we place the current mirror here in strong inversion, we get less variation than if we do in weak inversion. It's the opposite for differential pairs. So here it turns out that a high GM or ID is better for mismatch than is better. High GMOID is better than low. Okay, final slide. Noise. We also have a problem with noise. There are 3 types of noise that I've observed in transistors. Of course, you have thermal noise, simply random scattering of carriers in the conduction band, or random scattering of carriers. So sometimes the electrons will recombine with holes, and sometimes you get new electrons, and there's this rather random scattering of the silicon crystal also. That's going to give you a white noise. So it happens at all frequencies. Then we have what's called flicker noise. So sometimes the carriers that flow in the channel might get stuck in the oxide. Or actually, it doesn't have to be carriers in the channel. It can be simply modulating the threshold voltage. And this flicker noise is more like a random walk and has a power spectral density that is inversely proportional to frequency. So it sort of goes down. Yeah, let's not do that. Look at things about noise. But one more thing. Popcorn noise is something that has come in hard at about 55 nanometers. That's the first time I saw it. And it was a giant pain because it wasn't in the transistor model. It's not in the SPICE model at that point. So this is slightly different because you get a phenomena like what you're looking at here. This is a snippet from a book from Albert van der Ziel on noise in semiconductors or something. And it's weird because you can have actually the current in this case can stay low for minutes, or in this case milliseconds, but I've seen minutes, and then suddenly it jumps, and then it goes back again. And this is actually pure quantum physics. Here we have the Hamiltonian of, there's a Hamiltonian for the probability of electrons to jump from one state to another. Some of those states are quite rare, so they only happen once in a while. But if that state is in the silicon oxide or in the oxide of the transistor, it actually shifts the threshold voltage quite significantly because the transistors are so small now. And that means that these popcorn noise is also something that you have to think about. Okay, that's the final slide. This was a pretty long video about transistors, and I've only scratched the surface. But there's a lot more stuff to learn. Have a fantastic day.